we were talking about wear process, and we discussed that wear is the process of material removal from a surface as a result of sliding or rolling action. Okay, so first of all we have to understand that it is a material removal process. So if there is only plastic deformation, we do not call it wear. Okay, wear means the material has to be removed. So for example, if I have got this material and I hit with some other material here and there is some plastic deformation, okay, but there is no really removal of the material, then we don't call it wear. We call it plastic deformation or some other things. So this is one thing. So material removal has to be there. And another is sliding and rolling action. So it is always because of the sliding or rolling action, okay, or in some cases impact also, like impact action can also happen. So these are all impact. These are all mechanical actions. So material removal by, for example, a chemical reaction will not be considered as wear, okay, unless there is a mechanical process also involved. So for example, just purely chemical way of material removal, what is the process? What is it called? You remember the term?
Cutting process.
No, material removal, for example, happened because of some chemical action.
Corrosion.
Corrosion, yeah, corrosion is the one. So then it is called corrosion, not wear, if it is only material removal by chemical reaction. So, but if corrosion takes place in addition to some mechanical action.
Sir, ion displacement method and also wear take place in electrochemical machining, sir.
Yeah, so those can be considered as wear. Mechanical action must be there. So mechanical action, as I said, sliding, rolling, impact, and some plowing also we can say, which is also a result of sliding and rolling. So when it is combination of these two, then we call it wear, or sometimes people also call it corrosive wear. So many of the manufacturing processes are actually partly wear, partly corrosion. So they are called corrosive wear. Okay. One is electrochemical polishing. So here we employ sorry, this is not mechanical chemical polishing. So in this case we employ some chemical action, but also there is a mechanical action for the polishing process. So there has to be some mechanical action like sliding, rolling, impact, or as a result some plowing, plastic deformation can take place, so, and material removal should happen. So then it is called wear process. Important external factors affecting wear are interfacial friction. So friction, whether you measure it or not, friction is always there. Okay, so in some process we measure friction as well, but many times we do not measure friction during the process, but friction is there. So interfacial friction will be very important. Mechanical stress means load. So how much load? As you increase the load, wear will increase. Okay, but there is no kind of very fixed relation. There may be a sudden change in the wear rate as you increase the load. Relative speed is another important factor, because relative speed as well as the load, the pressure, will lead to some temperature rise. Temperature will rise, okay, which is known as the interfacial temperature. So interfacial temperature will rise because of frictional heating and also because of any other heat source nearby. So for example, in the case of any example you can tell me where in addition to frictional heating there are some other sources of heat while we are experiencing tribological action. So for example, engines, IC engine. We talk a lot about IC engine tribology or engine tribology. So here we have got cylinder and the piston. Okay, and this piston is moving in a reciprocation motion up and down, and there is a lot of sliding going on between the piston rings and the cylinder. Okay, but what is also happening is temperature is very high because here combustion is taking place. Because of combustion, very high temperature is created, and therefore the temperature at this cylinder wall is very high. So this is a case of where interfacial frictional heating plus the external heat will lead to very high interfacial temperature. And then depends on the, you have solid, liquid or gas. So solid, we know it is kind of sliding or rolling, but in the case of liquid it can be, for example, two-phase slurry. For example, in many of the mining industry, lot of material handling is done in the form of slurry, as well as in the chemical industry. So in that case, these liquid particles or liquid droplets will actually attack the surface. Okay, so in that case there is a lot of impact also happening. So in this case, not just liquid, but there will be solid particles as well. It can also be only liquid. Okay, because of liquid flow as well, there can be some wear process, especially in pipe bends. If you've got pipe with a bend here, so obviously this portion will be impacted again and again, and because of this impact, wear will take place here, and it often leads to failure of the pipes. Then gaseous also can happen. For example, in the gas pipeline, gases may contain some dust particles, so that's another thing. Okay, so when these two, because of liquid and gas, many times we use the word erosion. So erosion is also a part of wear. Okay, but specifically for liquid and gases, we use the word erosion, not wear. So this different terminology is used under different situations. Now defining wear, basically wear volume is proportional to the normal load, the sliding distance, and hardness of the wearing material. So it can be whichever material is wearing out, it is the hardness of that material. So V is given as kWd over H, and K is the proportionality constant, and it is also known as wear coefficient. So therefore K is VH over WD. So this equation is very popular. It is known as Archard's equation. So you should always remember this name. In the case of wear, this is the only model that has been very prevalent in the application. There are many other wear models, but many of those models are very specific to some specific conditions. But Archer's model is quite general and is used in many situations. So, so please remember this Archer's equation. The units of K, what will be the units of K?
Dimensionless, sir.
Yeah, it is dimensionless. This is also very important to remember that this K, which is known as wear coefficient, is dimensionless. As I said in the last lecture, that always often it is difficult to get value of H, so we bring H down here, then we call it specific wear rate, K over H. So K over H is known as specific wear rate, and in fact this is more popular than the wear coefficient. So whenever you conduct an experiment, you find out the wear volume and you know the load, how much load you applied, and also you calculate the sliding distance, and you can easily calculate a specific wear rate. And also remember that specific wear rate dimensions or units are this one, millimeter cube over Newton meter. It's not proper to use this as a meter, even though dimensionally it doesn't make any difference, but in a practical sense, because we always compare one thing to another, so units also should be same. So this is the proper units for wear, specific wear rate. So now another important thing to know about wear is, when you conduct a wear test is that when you conduct a test, then what will happen is some wear volume will there will be wear volume here. So for example, wear volume, and let's say with sliding distance d. So initially you will find that the wear volume is very high, okay? And then as sliding continues, the wear volume will go down. The rate of mass removal or rate of volume removal will come down. This happens almost in all cases, okay? But in some cases it will happen much more than the other case. And because most of the tribological devices or tribological equipments have got repeating action. So for example, in the case of bearing, on the same track or same path, the sliding continues, okay? But in some cases, only in few cases, you will see that there is always a new surface. So for example, road and the tire. So if this is the tire and this is the road, the tire always sees a fresh surface, a new road, right? Unless you move back and forth on the same road, your tire will always move forward, and as it moves forward, it sees a new surface, new road. But in most of the other cases, even brakes also have got the same issue, okay? For example, the brakes will be applied here and it will form some sort of wear track. So because of this repeating action that happens in most of the tribological devices or equipments, the wear volume initially will be large and then slowly it comes down, okay? So now if I run, let's say this is 1000, well, we can also present in the form of cycles of, okay? So let's say only 1000 is here, and here maybe let's say 10,000, okay? So for the same process, same combination of material and same other parameters, if I measure wear rate for only this much, and if I measure wear rate for this much, which one will be larger? Let's say this is situation A and this is situation B. So which value of wear rate, if I calculate the wear rate as given in this equation, let's say this equation, which wear rate will be higher, A or B?
So, sir, we cannot say no,
Why?
because sir, area under this curve is increasing, so volume is also increasing, and
No,
distance travel.
no, don't think about the area. Think about this one, the definition of wear rate, specific wear rate. So I have run something for 1000 cycles, okay, and here I have presented V, but mass loss or volume loss, you think about V. So as I said, in the first few cycles, it could be hundreds or thousands of cycles. The volume of wear is volume removal is large, but in the next, let's say, cycles, the volume removal is less. So if I measure specific wear rate by running this only for 1000 cycles, and if I run for 10,000 cycles, so which one should be more? Which wear rate should be more?
So initially, wear rate is more than it decreases.
Yeah.
Increasing
So
in cycle.
initially wear rate is more, and that is comes from this one, because most of the volume loss happened in the beginning, right? And we divided, W is constant, so no difference. So we divided V by a smaller number, okay? But if I run the same for 10,000 cycles, the volume initially was large, but after that it didn't change much. But D is changing, D is increasing, so this value will be lower, right? So we can say W specific wear rate for case A will be lower than W specific wear rate for the case B. For the same experiment, same material, everything is same. So this,
WA is greater than WB, sir. Written opposite.
yes. Yeah, that's right. So you're right. WA is greater than WB. Okay, so this is a very practical issue, practical problem, and we should always be aware. So whenever we are comparing wear rates of a material against another material and many materials, we should always be aware of this fact, and when we are conducting a test, we should make sure that the number of cycles is always same for all cases, so that we can compare in a proper way, in a more justified way. Okay. So all experimental parameters should be kept as same. This problem can happen in many other fields also. Have you conducted the tensile tests of materials?
Yes, sir.
Okay. So if you do a tension test here, for example, and let's say one specimen is like this, another specimen is very long. Okay, so you always call it the gauge length. So let's say gauge length is very long. So this is a tensile test we conduct for our materials like steel tensile test. So under one situation, which will always happen for at least for metals, the strain measured in this one is not same as this one. Let's say again call it A and B. So if I measure strain in A and strain in B, under some situation they are not same, even though in a stress strain curve you want to have the same strain. Let's say you want to plot a stress strain curve, but the strains cannot be compared between the two. You know what kind of situation? So in general, when we deform the material, we assume that there will be a uniform deformation, right? Initially elastic and then plastic deformation. There will be uniform deformation. But in reality, it is not uniform. What happens in a, let's say, mild steel? What will happen once it crosses the elastic limit?
Then say it got in plastic range and permanent deformation.
Yeah, but the problem happens is because of necking. Have you heard about necking?
Yes, sir. Cross section area is going very decrease.
Yeah, so necking will happen, and necking is concentrated within area here, within some volume of the material. It doesn't happen uniform. So even though we assumed there will be uniform deformation, but actually because of necking it became localized. So this is called localized deformation, localized plastic deformation. So this will happen here and this will happen here as well. So that means the rest of the material is not deforming, only plastic deformation is happening at this point. Okay, therefore uh, what will happen is uh, the new length or change in the length divided by the original length, right, is the strain. So the change in the length is happening almost same here as well as here once the plastic deformation starts and once the necking has started. So this remains the same, but the initial lengths are different. Initial length is small here and initial length is large here. Okay, so therefore this one will give us lower strain because small l is same but L naught is large in this case. So a practical problem you will find that epsilon B is less than epsilon A. The strain in the B specimen is lower than, okay. So this happens in almost all kinds of mechanical testing that we conduct. Okay, so this is a similar thing that we are experiencing here in the case of wear measurement. So as a standard, please keep all the parameters including the sliding distance as fixed. So now we have some data here. Again, whenever I write here, please know that this is the reference where I am taking this figure from. So this is from John Williams' book, figure 5.1. But the original data may be from somewhere else. So I also write here because we should give credit to the original authors of this work. So this was Hurst and Lancaster in 1956 from a research paper. So here we have got wear rate and electrical contact resistance for a leaded brass pin sliding against a hard stellite ring. So stellite is some sort of hard material, hard, I don't know the composition, but I think hard steel, and this is leaded brass pin. That means brass which has been added with some lead inside. Okay, so here we can see that wear rate, this one is wear rate, this one, and we also have electrical resistance. So now we can see that the wear rate is not fixed, it is changing quite a lot. It is changing with the load. So initially it was lower range. So for example, at this the wear rate was 10 to the power minus 5, which is low, not very low, and all of a sudden there is a sharp change and then the wear rate goes very high. So this is 10 to the power minus 4, which is higher than this one, and this is 10 to the power minus 2, very high. So wear rate is changing quite drastically, and this is changing by orders of magnitude. So from minus 5 to minus 4 to minus 2. So this type of behavior is very frequently observed in most of the materials. So this part is known as mild wear, and this part is known as severe wear. So just a very informal kind of differentiation between mild wear and severe wear. At what value of normal load it will happen, it depends on the material pair. Okay, so this is not a fixed. It doesn't mean that all wear process will have this kind of transition from mild wear to severe wear at, let's say, 9 Newton. It's not that, or 10 Newton. This is for this specific case, it happened like this. So normally you will see that for mild wear, it results in extremely smooth surface. So this will lead to smooth surface, and sometimes even smoother than the original surface. So the process, for example, polishing, when we conduct polishing often happens in the mild wear regime. Okay, so during the polishing you should keep the wear process in the mild wear regime. You should not keep it in the severe wear, otherwise polishing will not give you a good result. So naturally it gives a smoother surface, and the debris is extremely small, typically 100 nanometer. So size of the debris material is in the range of 100 nanometer. So it is very small, and that's why when you do a polishing, you cannot actually pick the wear debris. You cannot. It is there. It is in the liquid that you use, but it is very small. So in this range. And another data we have got here is electrical resistance. So why there is this data has been presented? What is the reason for this?
Sir, for knowing microstructure of.
No, not related to microstructure. It is a way to actually assess the wear rate, the wear happening at the surface. So for example, if you have got, and it is used for metals only, metal 1 and metal 2. And let's say the wear process is happening, so there is a interfacial sliding going on here. Then what people do is we connect this to a voltmeter and we pass the electricity. Okay, so because there is a connection, two metals are in contact with each other, obviously there will be electrical passage. Okay, so we can measure the resistance of this contact. So what happens is, as we increase the load, the electrical resistance was going down, means conductivity was increasing, right? This interface was becoming more and more conducting, resistance was going down, and near the transition actually the resistance became very smaller value, a very low value, and almost like a fixed. That means conductivity was high here, electrical conductivity, so reverse of resistance. So that means when it was in the mild wear regime here, resistance was very high. That means the electricity was not passing through here, which also means that they were not in contact, right? The contact was low, because if contact is high, then obviously the current will pass through and the resistance will be high. Resistance will be low. Okay, so here the resistance is high, that means contact is not good, and here resistance is low, that means contact is very good. Okay, so that means during the mild wear regime the resistance will be high resistance will be high, and contact will not be very good. And in the severe wear regime, resistance will be low and contact will be good. So in a way, we can use this contact electrical resistance as a method to find out the wear process. But as I said, it can be done only if both materials are metals and conducting electricity. For non-metals like polymers and composites and ceramics, it's not possible. Okay. So in the mild wear regime, the resistance is high. When we go to the severe wear regime, then what will happen is wear rate all of a sudden changes to a very higher value, and it may just continue. It may be a fixed, or it may continue to increase. Generally it will continue to increase because some transitions are always taking place and resistance is very, very low. That means there is a good metal to metal contact. So this just indicates that these two metals are in contact very intimately, therefore electricity is passing through. And this also indicates that plastic deformation is taking place, and wear is also taking place. So this method of measuring wear situation is used in many examples. So for severe wear results in rough surface, whereas mild wear leads to smooth surface. So if you see a rough surface, then that means wear is in the severe range. So for example, in a machining process, you don't want the machined surface, the new surface, to be very rough. But if it is rough, that means the parameters need to be changed so that you bring it down to the mild wear regime. Okay. And there will be large metallic wear debris particles. So wear debris particles size may be 0.01 millimeter in diameter. Low contact resistance, as we already discussed, the contact resistance is low. So this is a very good way of understanding the wear process. But there are many more ways that wear can take place, but this is one very initial way of understanding it. So here in this table, let's see the wear coefficient. So we have got wear coefficient, not a specific wear rate. So therefore there is no dimension of it. It is dimensionless. And pin on this test was conducted, and all in air. And the coefficient of friction was also measured, which varied between 0.18 to 0.8. So mild steel on mild steel gave very high wear rate, as you can see, 10 to the power minus 3. But when you change to another material against mild steel, the wear rate was lower. Sorry, this one. Yeah. So wear rate was reduced. Okay. So for them, for example, 10 to the power minus 7 for polyethylene is very low wear rate. PMMA also 10 to the power minus 6, and other metals are in this range, minus 4 to minus 5. But one exception is PTFE. Teflon has got high wear rate. Okay, so this kind of data tells us few points. First important thing is predicting or modeling wear by any analytical or computer simulation method is extremely challenging. Okay, although people are trying, and I think we will have one industry presentation on this one, on modeling wear using some computer simulation process. But in general, we have understood that modeling wear is very challenging. Another thing we can understand from this table is numerical values of K is always much lower than unity. Okay. So these are all the numerical values of wear coefficient, and all of them are much lower than 1. Okay. So always in this range. And as I said, if it is in this range, 10 to the power minus 7, this is a good situation because wear rate is very small. If it is 10 to the power minus 3, it is not a good situation because wear rate is very high, and you might get numbers in between. So you can see that there is a order of difference between different wear rates, but friction is not changing much. Friction is changing only from 0.18 to 0.8. So this is a very important thing to remember, that mu doesn't change much, but for very small change in mu, wear rate can change by orders of magnitude. So when you are doing any kind of modeling or simulation where you need the value of mu, right, and often people take some value, let's say 0.3 for steel, and they can do some calculation. Okay, but you should know that if it is changing from 0.3 to 0.35, it makes a big difference, both in terms of wear as well as in terms of energy consumption. Okay, similarly from 0.3 to, if I make it 0.2, it is such a big difference. So in terms of mu, we should be careful in choosing what kind of value of mu we take. Okay, very minor change in the mu will make very big difference to the final result, which may be wear, which may be energy consumption, and so on. So wear rate can vary by several orders of magnitude, and this is true not only for the dry condition but for also lubricated condition. Another thing we have understood is that similar materials will give you high wear rate. Okay, as well as friction also, we know that friction was very high. Sorry?
Very high for similar metal.
So, sorry, can you say again? Sorry.
Yes, sir. Coefficient of friction is high for similar metals.
Yeah, it is true. So last time we were talking about friction. So friction was between mild steel and mild steel was 0.5 or more. It will be always in the higher side. Okay, and that also indicates that wear is very high. So whenever you are combining two materials together, never select same material. It will happen for all materials like brass on brass, or even for polymers, polyethylene on polyethylene. So always select two different materials, and obviously we went through all the solubility rules and so on to select the best material combination. And another important thing we should remember is there is no simple correlation between friction and wear. Although we would like to have a very nice one equation where we can relate mu with W, specific wear rate, but there is no such simple relation. The relations that you might find in some books or some other research papers, they are very specific to some certain conditions, certain situation, not a general equation. But in general, we can say that high friction will lead to high wear, or low friction will lead to low wear. But again, there are exceptions to this rule as well. For example, one very good exception is PTFE. We all know the PTFE gives a low coefficient of friction, right? What is the coefficient of friction of PTFE against let's say steel? What will be the friction coefficient? So don't know. So this coefficient of friction can be in the range of 0.09 or 0.08, something like that, or 0.6, or even lower than that you can get. But friction, but wear rate is very high, as you can see. So there are exceptions to this rule as well, that high friction leads to high wear, or low friction leads to low wear. This is a general rule we can accept, but there are some exceptions. Okay, so it is almost 11:46, so we will stop here. Any question on this?
Sir, as in case of PTFE, we have a value of mu as less as even less than 0.1. So the
It is
kind of wear
possible.
that will occur
So yes, you
when
said
we have a
correctly.
surface like steel and PTFE.
Yeah, so
What kind of wear will occur as we have a very low value
okay,
of
so yeah,
coefficient
we
of
will
friction,
talk
like
about
0.01.
the wear mechanism. Under different situation we have different wear mechanisms, and this mechanism controls the level of wear or the rate of wear. Okay, so PTFE
Sir,
is, yeah,
whether the wear will be very less based on the statement that you have written below, like very high friction will lead to high wear.
uh, yeah, this is a
In
general
case of PTFE,
for PTFE. No, in PTFE,
Exception.
low friction but high wear rate. Okay, and with PTFE you cannot achieve high
exceptional behavior.
friction. Yeah, yeah, tell
Okay,
me
sir.
again. Okay, so different material combination will give you different kinds of friction values, and also corresponding the wear values. But without talking about which material we are thinking, in general we can say that if friction is high, wear will be high. If friction is low, wear will be low, which is our normal understanding. But there are some exceptions, and PTFE is one of that exception.
Okay, sir.
Any other question?
No, sir.
No, okay.